argillaceous lime from the French word argile for clay. Per the European norm 459, that's the standard, the European standard for building limes. They're categorized into three grades right now as of the last specification. They are NHL2, which traditionally was a feebly hydraulic lime, a very soft hydraulic lime. Your NHL 3.0 moderately hydraulic limes, and then your 5s, your eminently hydraulic limes. Now these numbers basically refer to the lime's crushing strength or the mortar's crushing strength at 28 days in the laboratory mix, measured in newtons per square millimeter. So if you use the guide 145 psi per newton, you're looking at an NHL2 having a compressive strength of about 290 psi at 28 days. So then so forth and so on. I'm trying not to do 3.5. A few examples of historic hydraulic limes in the U.S. Some people say that hydraulic lime wasn't produced in the U.S., that it was a European thing. Couldn't be further from the truth. We certainly know from Riverton Hydraulic Lime Works, which just closed down less than a decade ago, that hydraulic limes were produced in the U.S. But before the Civil War, the antebellum times, most all lime was a cottage industry. If a bricklayer needed mortar, he quarried his own limestone, or he got his limestone, he burned it in a little kiln, or a farmer burned it in his kiln, and they made it. Now if that limestone had silica or aluminates in it, you were going to be making a hydraulic lime. And if the mortar you were making, if you were using a hot lime mortar, not a lime putty mortar, but a hot lime mortar, you would just notice that this lime is really good. It makes a very strong material. Now, of course, you cannot take a hydraulic lime, burn it, or limestone, burn it, and then slake it to a paste, because that paste would start to set. But if the majority of historic mortars were made in that hot mix method, you wouldn't have any problems. Hey, how's it going? So pre-Civil War, you're looking at a cottage industry localized examples. James Madison's Montpelier, a project that we just finished up. We did quite a bit of research into the original limes that were produced there. That was a argillaceous limestone, so it had a certain amount of silica and alumina in the limestone matrix. And we actually produced a hot lime mortar from the actual same stone that Madison was using. It was a fantastic project. But we were making a true like-for-like material. It was Madison's mortar. This advertisement over here is from the 1870s, if I'm not mistaken. There's a date kind of up there in the corner. But it's for an agent for the Alabaster Lime Works in Atlanta, Georgia. I happened to stumble upon that online one day. So we know that hydraulic limes were being produced in the U.S. At least in the 1870s in a commercial operation. Williams Hall. How many Hokies do I have in the room? All right. I'm a Hokie myself, but any Wahoos in the room? Okay, it's half and half. We'll say there are more Hokies in the room. Williams Hall, there on the drill field there at Virginia Tech. I was actually called in to do some consultancy at Virginia Tech. We were looking at some of these buildings, and the mortar was great. I mean, it was some of the best mortar I had seen, and buildings, and it was unlike anything that I had really seen for that time period. I'm used to seeing Portland cement-based mortars when we're looking at buildings from the 1960s. We happened to stumble across the original specification for the project, and the mortar mix was a hydraulic lime sand mix. And they realized that a hydraulic lime mortar would perform far more superiorly than a cement-based mortar with this type of stone that they were building with. And actually today, with some of the buildings that they're building on campus now, they are having problems with their mortar because they're using a Portland cement-based mix versus lime-based mix. Natural cement, I'll just take a few minutes to talk about natural cements now. They are almost like the big brother or the big cousin of hydraulic limes. These are made from limestones that have so much silica in it, and so much alumina in it, that when you burn it, you don't have any lime left over. It's all hydraulic compounds. So you can't slake it. If you add water to it, it will start to set. It will start to get hardened almost immediately. It will start to harden almost immediately. So the material is ground up to a powder and supplied that way. And that, at the end of the day, is the main difference between a lime and a cement. A lime is something that's slaked, and a cement is something that's ground to a powder. Of course, there's a lot of chemistry too, but for the purposes of this discussion, we'll just call it that. Vicat Comte natural cement. This is a French natural cement. I had the pleasure of visiting them last year, actually. They have been producing natural cement uninterrupted since the mid-1800s. Of course, y'all know Louis Vicat. Anyone read Vicat? I know Brian Green in the audience has read Vicat. Vicat was an engineer to Napoleon back in the 1800s. He established the hydraulicity index. And also did quite a bit of survey throughout France in limestone and whatnot. And they determined that this stone right here was very, very good for marine works and engineering works. And his son actually set up the company there, hence the name Vicat. The production process on Vicat is very similar, or natural cement is very similar. And just as an aside, here in the U.S., natural cements were produced as well. The Rosendale cements from New York were very, very common in government work and marine work of the Erie Canal, Brooklyn Bridge. All of these big engineering projects for the 1800s were built with a Rosendale cement. Although you had other natural cements being produced throughout the East Coast. There's kind of a seam of cement rock that just comes right down the coast. But what we have here, you have a deposit, a raw limestone deposit that's extracted. It goes to the kilns where it's cooked. The resultant quicklime, if you want to use the term, or burnt cement rock, is then crushed and ground up where the powder is shipped off. Now, this material is extremely hydraulic. If you add water to pure natural cement, the set starts to take place in about 3 minutes. And it is at a hardened state in about 5 or 7 minutes. It's extremely fast setting. At 28 days, if I'm not mistaken, you're looking at compressive strengths of upwards of 5,000 psi. So very, very hydraulic, very, very tough stuff. And traditional. You often hear the comment that you can't use a historic mortar because they're not strong enough. Well, we can make historic mortars that range from 100 psi to 5,000 psi without any Portland Smith whatsoever. So to say that historic mortars are too soft, I just don't take that argument. The kilns at Vicat have actually been in continuous use since the 1870s, 1872. I took that picture. It was actually a pretty big thrill to be standing on top of these century-old cement kilns. Now this phase diagram kind of shows what you have as far as mineralogy in the raw limestone, and then what happens over time, or rather over temperature. So at its base form in Celsius, 400 degrees Celsius, you have calcite, that's your calcium carbonate, your limestone. Your quartz is your silica that we've been talking about with hydraulic limes. And then you have your clay minerals, these silicates and aluminates and whatnot. Now, as you start to cook it, a couple of things start to take place. That calcite starts to convert over to lime, calcium oxide. Your calcite and quartz start to combine together, form a whole new compound called dicalcium silicates, or B-lights as they're known. They're the material that makes hydraulic limes get hard when they're hydrated. And if you're burning an argillaceous lime, you start to form these aluminates and these ferrites. You do have to be careful, even with traditional materials. You can have all the good intentions of the world, but you can start to mess stuff up if you start burning too hot. Because after you go over about that 1200 degrees with a hydraulic lime, your aluminates and your ferrites start to go into a liquid phase. Your B light starts to combine basically with another silica and form